Okay, let's get into this. We're doing a deep dive today, focusing on some real basics, but, fundamental stuff. Volume and surface area.
Yeah, absolutely core concepts.
And the idea is using the material we've got to kind of cut through to what really matters, the key takeaways on these geometric ideas.
And it's amazing how powerful they are, right? Just these measurements tell you so much about, well, everything around us. The source material defines volume simply as the space a body occupies.
Right. And it makes a good point. For solids, it's the space the actual material fills. But for hollow things, like, say, a box, you've got the outside volume, the space inside.
And the material volume is the difference.
Yeah.
It's about which space you mean.
Exactly. Precision matters there.
And surface area. The material presents that pretty straightforwardly, just the total area on the outside.
Like wrapping paper.
Sort of, yeah. Add up the areas of all the faces. That's it.
And the source connects this to stuff we see all the time. Matchboxes, bricks, good examples mentioned.
Which leads right into the cuboid. That's the first shape they really break down.
Described as a body with 6 rectangular faces. That brick or matchbox again.
Yep, picture it. And the key features highlighted are 12 edges, 6 faces.
And crucially, opposite edges are equal, opposite faces have the same area. Very symmetrical in that way.
And the formulas are neat because of that structure. Volume is just length times breadth times height.
LABEH. Easy.
You're basically stacking up that base area through the height.
Makes sense. And the total surface area. You add up all 6 rectangles.
Which, yeah, simplifies nicely. It comes out as 2 times length times breadth plus breadth times height plus height times length.
So 2 pound plus BH plus HL.
Got it. And there's a solid example in the text. A cuboid, 25 centimeter by 20 centimeters by 12 centimeters high.
Oh, okay.
Plug those in, you get surface area, 2080 square centimeters, volume, 6,000 cubic centimeters, just works.
Okay, clear enough. But what if? What if you make that cuboid perfectly balanced? Length, breadth, height, all the same.
Ah, well, that's the special case, isn't it? That's your cube. L equals H. So every face is now a square.
Which must make the formulas even simpler.
Oh, definitely. Yeah. If L is the side length, each face is just L squared area.
Okay.
And there are 6 of them. So total surface area is just 6 times L squared. 6 and 11.
Nice. And volume.
Even easier. L times L times L. Or L cubed.
Very compact. The material gives a cube example too, right?
Yeah, side length 16 centimeters. Works out to total surface area. 136 centimeters volume. 4096 centimeter SIAMs. Efficient shape, efficient math.
So where does this stuff actually, get used? Practical side.
Well, the source immediately jumps into that, like calculating the area of the 4 walls of a room.
Ah, okay. So you ignore the floor and ceiling, like a hollow cuboid kind of.
Exactly. And the formula for just those walls is 2 times length plus breadth, all times height, 2L plus BAH.
Makes sense. It's the perimeter times the height.
Precisely. And they use an example. A room, 8 meters long, 4.5 wide, 3 high. That formula gives you 75 square meters for the walls. Super useful for, say, painting jobs. The text even mentions calculating distempering costs based on that.
Right. You need the area to buy the right amount of paint. That's practical.
And it goes further, using volume to find missing info. Like, if you know a tank's volume and its base area...
You can figure out the depth.
Exactly. The example calculation ends up finding a depth of 2 meters. Useful.
Or, another classic, how many small things fit into a big thing? Volume comparison.
Like the bricks example.
Yeah. Calculating how many standard bricks you need for a wall of certain dimensions. The text works it out to 78,705 bricks.
Wow. So basic geometry underpins actual construction planning.
Fundamentally, yes. Volume and surface area are everywhere in building and design.
So wrapping this part up, what have we kind of distilled here? We've got volume as space occupied, surface area as the outer skin.
Broken down the cuboid and its special case, the cube. Got the key formula.
And seen how they apply directly. Rooms, tanks, bricks, real-world stuff pulled straight from the source material. It's about getting that quick, clear handle on these geometric tools. Pretty powerful for such simple ideas.
It really is. And it makes you think. That idea of empty space we started with, is it truly empty? Or just volume waiting to be filled? How much can we understand just from knowing these few dimensions, the inside capacity and the outside area? From tiny boxes to the rooms we live in. Makes you wonder, doesn't it?